Good evening. Today we are going to discuss bending trace and shearing trace. And if time permits, we will go for deflection of beam also. So in this session, we are going to solve problems. So this problem is from GATE 2016 for 2 marks, 1 meter into 10 mm into 10 mm cantilever beam. So cross section of a beam is a square cross section is subject to uniformly distributed load 100 Newton per meter over an entire span as per unit length. Over an entire span per unit length. Okay, the normal stress in MPa due to bending at a point P is. So here you can see cantilever beam is given. Actually, diagram is not given. We need to convert statement into diagram. So cantilever beam is given and uniformly distributed load over an entire span of a beam. Length of a beam 1 meter is given. Cross section of a beam is a square cross section. Okay, and we need to find out that P point is at the upper fiber. Okay, so we need to find out the bending trace at upper fiber. So we know the formula, that is flexure formula, M by I equal to sigma y equal to E by R. Right, M means maximum bending moment, I is the moment of inertia, sigma is the bending trace, and y is the distance from the neutral axis, distance of extreme fiber means upper fiber and lower fiber from the neutral axis. Okay, neutral axis is the axis of a cross section with a neutral layer, and neutral layer means at that layer there is a no tensile and compressive stress. Actually this bending trace is nothing but the normal trace. Okay, so first we will see what is meant by bending trace and shearing trace. Due to external loading, beam tends to bend. Generally whenever a load is a transfer loading, due to external loading beam tends to bend or deflect, and internal traces resist its bending. The process bending stops when every cross section set a full resistance to the bending moment. Means whenever we apply the transfer load on a beam, that load tends to bend the beam, but due to cohesive forces in the beam material, that cohesive forces resist the bending of a beam, and at a certain level, at a certain stage, that every cross section set up full resistance to the bending moment. Means partially at when we apply the load, it is going to bend, but at a certain level that bending gets stopped due to full resistance developed in the beam due to cohesive forces. Okay, so that stresses is called as the bending stresses, and in shearing stresses, the stresses induced to resist the, or we can say the stresses induced to resist the bending moment are called the bending stresses, and the stresses induced to resist the shear forces are called as a shearing stresses. Here in this problem, we need to find out the bending stresses at the top fiber, and we have gone through this flexure formula, or we can say bending stress formula, M by I equal to sigma by y. Right, now we need to calculate maximum bending moment. Maximum bending moment, that is mean M. Okay, so how to calculate maximum bending moment? So just if we draw the free body diagram, easily we will get the bending moment. So to draw the free body diagram, So we need to convert UDL into point load. Now UDL intensity is 1,000 Newton per meter and length of beam is also 1 meter. So I will write here 100 Newton. Total load is 100 Newton only. Okay. And here is the fixed support. So we need to take three reactions. One vertical, another horizontal, and third is the movement. Okay. Here I assume that movement is anti-clockwise. You can take clockwise also, no problem. But beam is going to bend in downward direction. For that purpose, I have taken here in the anti-clockwise direction. Let this movement is a MA. Then this is AY force. We need not to calculate AX force because if we use equilibrium condition, summation of x equal to 0, x value equal to 0. Okay. So just I will copy this free body diagram for the further calculations. So to calculate the bending stress, we should calculate here bending stress means sigma. So to calculate the sigma, we should know the value of maximum bending moment, then moment of inertia, and extreme fiber distance. Right. So here P point is at the top fiber, and Y is the distance from the neutral axis. Here neutral axis is at the center. So means at a distance of 5 mm. So Y equal to 5 mm. M, we need to calculate maximum bending moment. So if we use the concept of shear force and bending moment, then we need to take section here at the left side and the right of A point and at the end of B point. So we need to calculate bending moment at 2 points only. So bending moment at A, just left of A, just left of A, that is 0. So you need not to write actually, so I will write directly right, just right of A equal to minus MA. So we need to calculate the value of MA and bending moment of at B equal to 0. So as per bending moment section, bending moment is maximum at just right of A. Bending moment at B point means at extreme right point equal to 0. Okay. So now we need to calculate this bending moment. So we can calculate this moment by taking moment about point A. Okay. So by taking moment about point A, we can calculate taking moment about point A, that is equilibrium condition, then moment of 100 Newton force, 100 into 0.5. Okay, 100 into 0.5, and this moment is a anti-clockwise, clockwise, so positive, and movement, this movement will we need to include minus MA. Sorry, I will write here small a equal to 0. So in this way we'll get the value of MA. Value of MA is value of MA is 100 into 0.5 means 50 Newton meter. Sorry, 50 Newton meter. That is the maximum bending moment. Okay. Now we got the value of M. Now to calculate the value of I, how we can calculate the value of I? So by using standard formula here, because cross section is a rectangular, so sorry, square. So BD cube by 12. B means breadth, D means depth. B equal to 10 into 10 cube divided by 12. So calculate the value of I. 10 into 1000 divided by 12. So 833 point, value of I equal to 833.33. Okay. Mm raised to 4. Mm raised to 4. Okay. Now we need to calculate the value of Y. Value of Y equal to, Y is nothing but the distance of extreme fiber from the neutral axis. Now here neutral axis is the at a distance of 5 mm from the top. Okay. So we can say Y equal to 5. Just put the value of MI. This is the neutral axis and this distance is called as Y. Upper fiber or lower fiber from the neutral axis. This distance is a Y. Okay. Now value of M is 50 Newton meter. So I will convert it into Newton mm. 50 into 1000. Okay. Divided by I. 833.33. Okay. Equal to sigma and divided by Y equal to 5. Now calculate the value of sigma. into 1000 भागिले 833.33. Okay, into 5. So in this way we got the answer 300 MPa. Sigma equal to 300 Newton per mm square. 300 MPa. So this is the answer. or the bending trace at a point P, upper fiber. Hello, do you understood how to calculate the bending trace? Okay. Now we'll go for the next problem. Ah, similar problem. This is from GATE 2010. 10 is against. This question is for 2 mark. A cantilever beam 2 meter into 10 mm by 10 mm means length of a beam is given 2 meter and cross section is 10 by 10 means cross section is a square. It carries transfer load of 10 Newton at the center. Considering only bottom fiber of a beam, the correct representation of a longitudinal variation of a bending trace is. So here four options given: 60 MPa, downward 400 MPa, 60 MPa, but here second degree curve is given, and here 400 MPa and second degree curve is given, right? Now M by I equal to sigma by Y. Okay. Now this bending trace is directly proportional to the Y. Bending trace is directly proportional to the Y. If we take this M by I, so if we write here in terms of a Y, you will get the idea. Y equal to sigma into I divided by M. Y equal to sigma I divided by M, or we can say sigma equal to M by I into I. Sorry, I have written sigma equal to M by I into Y. So here sigma is directly proportional to the Y, means power of Y is a 1 only, so it shows a straight line equation. So directly we can neglect these two options, C and D option. It shows the curve, second degree curve, right? Now we need to calculate the bending trace at the bottom fiber, means at the extreme fiber. Again we are going to use this same formula, sigma equal to M by I into Y. Now we need to calculate bending moment just right off this A point. Again this bending moment will be 10 into 1. Sorry, bending moment will be, okay, we'll calculate the bending moment. First we'll draw the freeboard diagram. Similar to this, just here instead of 100, how much value? 10 Newton value is given. Okay, value is 10 Newton, but that is not a point load here. In earlier diagram, that is the point UDL load, but here point load is given. This is the cantilever beam, means if we are applying the load from the upper side, so the upper fiber will be in a tension and lower fiber will be in a compression, right? Do you understood? The upper fiber will be in a tension and lower fiber in a compression, because we are applying the load from the top side. Okay, so it will bend like this. This curve will bend like this curve, this beam will bend. So this upper fiber means top part of the beam is under tension, and bottom fiber means bottom layer of a beam will be in a compression, right? And compression zone always we show from the below the neutral axis. Sorry, not a compression zone. That compress value we show the behind the y-axis. Okay, I will show you. So sigma equal to m by I into y. First we need to find out the value of ma. So again value of ma equal to 10 into 1. So value of ma is a 10 Newton meter. Okay, 10 Newton meter. Value of ma is a 10 Newton meter. So I will take it as 10 Newton meter, means 10 into 1000. Okay. Then value of I. Again, it is a square cross section, similar to earlier problem. Moment of inertia is 833.33 square mm raised to 4. So just I will put the value here. Okay, and value of y is again value of y is a 5. But here we need to consider bottom fiber. Okay, I will show the cross section. This is the beam cross section. This is a line diagram of a beam, and at the center there will be a neutral axis. We need to find out the bending trace at the bottom fiber. Means we need to find out the compressive bending trace. Okay, into y, that is 5. Now calculate the value. 10 into 1000 divided by 833.33 into 5. So value is, okay, once again we check the value of 10 Newton. Okay, 10 into 1 by I into 1. Sorry. Sorry, we need to calculate bending moment here also. Okay, we need to take section to calculate the maximum bending moment. Just right of A and add this point load also. Okay, now we'll see which value is more. So bending moment at right of A, just right of A, equal to minus 10 Newton meter. Okay, and bending moment at center that take that point is a C equal to minus 10, then bending moment of AY force, that is clockwise. AY force is 10 into 1. Ten into 1 again 10. So bending moment at center equal to 0. So maximum bending moment is a 10 Newton meter. Okay. So 10 into 1000 divided by 833.3 into 5. So answer 10 into 1000 divided by 833.33 into 5. Answer shows 2.40. Okay, we'll check. We'll check the answer. Bending press. Okay. Actual answer is a 60 MPa. I will see later on. Our answer is 2.40 MPa. 2.40 MPa. Yes, 60 MPa. Prachi, how you get the 60 MPa?
Actually, sir, I calculated that sigma
Yes, huh.
means hello.
With the same formula, you calculated
Yes,
the
sir, I calculated with the same formula.
value of I is the right 833.33. You have taken that maximum bending moment different. His calculation is right. 10 into 1000 divided by 833.33 divided by 5. Okay, we'll see next problem. Now, to find out the deflection of a beam, a cantilever beam with a flexure rigidity of 200 Newton per meter, 200 Newton meter square is loaded as shown in a figure. The deflection in mm at the tip of the beam is, means we need to find out the deflection at the end of this cantilever beam. So we can solve by our conventional method, means we need to take section here by regular method. Then we need to write down the bending moment equation. Then next step, we need to find out the value of constant, integration constant C1, C2 by using boundary conditions, right? But these are the some standard conditions. You can match with this standard condition. This second, you can see here, load P is applied at a distance from the left hand, okay, and maximum deflection. So by observing this beam, we can say maximum deflection will happen at the end, right? So maximum deflection equal to PA square into bracket 3L minus A divided by 6 EI. Value of EI is given 200 Newton dot 200 Newton meter square. Okay, so in this way we can find out the maximum deflection by using this formula, or also we can solve by our conventional method, but it will take a time. So please go through this formula. This formula is applicable for the cantilever beam, the standard cantilever beam. Okay, so we'll solve by using this formula delta max. So I will write here maximum deflection equal to PA square, means our load is a 500 Newton. Okay, I'm going to use this second formula, 5 PA into A means 50 square. Okay, three L by A, 3 into 100, L is 100 minus A 50 divided by 6 EI divided by 6 EI. Six into EI, value of EI is given 200, but we need to convert it into Newton mm square. So multiply by 10 raised to 6. 10 raised to 6. Now calculate the value. So this will be maximum deflection. So D max equal to, or we can say D at the end point, D delta at the end point B. Okay, D max equal to, now calculate 3L minus A, 3L, 300 minus 50, 250 into 500 into 50 square divided by 6 into 200 into 10 raised to 6. So we get the deflection 0.264, that is right answer, 2.260 mm. So to solve the deflection problem, generally, most of the times, all the problems on the basis of the standard cases, either cantilever or simply supported beam with a center point load, with a end point load, with a uniform UDL, uniformly varying load, or concentrated movement at the end. So just we need to remind this formula. Otherwise, we can solve this problem by using our conventional method. That is, we need to take section at a distance x. This is also simple method, but it take a time. We need to take a section at a distance x. Then we need to write down the bending moment. So here bending moment equation will be AYX, okay, minus MA into x raised to 0 and 500 into x minus 50, okay. Then we need to integrate the equation. After first integration, we will get the equation for the deflection. Then again we need to do integration. Then finally we will get the equation for the deflection. And then we are going to apply boundary conditions. Boundary conditions means we need to vary this x at the support. Suppose we move this section at the fixed support. At that time we can say x equal to 0, y equal to 0. Means at this support there is no deflection, because this purpose of support is to avoid the deflection. So we can say x equal to 0, y equal to 0. And second boundary condition, x equal to 0, dy by dx is also 0, because at this beam is going to bend like this, and at this fixed support deflection is also 0. So second boundary condition will be x equal to 0, dy by dx equal to 0. This boundary condition will be useful to find out the value of constant of integration, that is C1 and C2. Generally we take notation C1 and C2, okay. And after putting that value, we need to put in a deflection equation x equal to 100 mm to find out the deflection at the end point, okay. So that is the conventional method. It need that method is a time consuming, but you will get definite answer. Here you need to remind number of formulas for the standard cases, okay. Do you understood? Yogiraj, Prachi, do you understood this problem of deflection of beam? Okay, we'll solve one problem by conventional method also. I will see next problem. Okay, a cantilever beam with a square cross section of a 6 mm side is subjected to load of 2 kilonewton normal to the top surface as shown in figure, okay. The Young's models of the elasticity of the material of a beam is 210 GPa. The magnitude of slope in a radian at Q 20 mm from the fixed end is. So in this case we need to find out the slope at a distance 20 mm, okay. So again we can use the standard formula, but we will solve it by the conventional method, okay. So I will take a section. First we need to draw a freeboard diagram. Why conventional method? Because there are very few standard cases. If this load is applied, if two loads are applied on the cantilever beam, then there is no standard formula to calculate the deflection or calculate the slope. So we should aware of the conventional method also. At the fixed support, we need to take three reactions: horizontal, vertical, and movement. Now here value of Ay equal to, directly by observation you can write value, that is 2 kilonewton. Value of Ay is 2 kilonewton because only one vertical force on the beam, that is 2 kilonewton. It is acting downward. So this Ay value is a 2 kilonewton upward, and movement equal to 2 into 100 mm distance. So 2 into 100, 200 kilonewton mm. Okay, 200 kilonewton mm. So I will write here value 200 kilonewton mm. Okay. Now convert this kilonewton into Newton. Now next task is important, that we need to take a section. Here I will take a section. Now let this distance is x from the left hand. Okay, now we need to write the bending moment equation. That is EI d square y by dx square equal to, EI means vector rigidity, just I will write the equations and write down, or I will write boundary conditions. Now moment is minus 200 into 10 raised to 3. I will write here 1000 Newton mm. Okay. And for movement we need to write x raised to 0 because movement is already in a Newton mm. So for calculation purpose I will write here x raised to 0. X raised to 0. That is important. X raised to 0. Okay. Then next compartment. So just I will draw here vertical line. And next value is so now moment of this 2 kilonewton force means 200 kilonewton, 2000 kilonewton, and that moment of this force about section S is a clockwise. So plus 2000 into x. sorry, into x. So this is the equation. Now we need to integrate this equation with respect to x. Integrate with respect to x. So here we'll get ei dy by dx. Now integration of this minus 200 into 1000, here we'll get the value x raised to 1, 200x square, and plus integration constant, that is c1. Once again integrate this equation to get deflection equation. Integration with respect to x, ei. Now here we'll get ei y. Integration of dy by dx equal to y. Okay. Now here 200x square by 2I. This is 2 factorial. The rest 2. Okay. Divided by 2. Sorry. Okay, then c1 into x and 200 into x cube. Now here we'll get x cube divided by 3i, 3 factorial. Okay. Right. Now to calculate the slope, we are going to use this equation number second, but for the equation number second we need to calculate the value of c1, and here value of x will be 20 mm, because our x we have taken here section at a distance x, but we can move this section from 0 to 100 mm, and we need to calculate the slope at a distance of 20 mm. So we are going to put x equal to 2 in this equation. Okay, but first we need to find out the value of c1. C1 is a constant of integration. So two boundary conditions, we know that two boundary conditions here, c1x plus, sorry, I need to write here c2. Okay, so first boundary condition for the cantilever beam, x equal to 0, y equal to 0. X equal to 0, y equal to 0. And second boundary condition, x equal to 0, dy by dx equal to 0. Dy by dx equal to 0. Okay, so let put this condition in equation number 3. This is equation number 1, this is equation 2, and this is equation 3. If we put x equal to 0, y equal to 0, we'll get directly c2 equal to 0. Okay. Now second boundary condition, x equal to 0, dy by dx equal to 0. Here if we put the value of dy by dx equal to 0 and x equal to 0, so here also we'll get c1 equal to 0. So for the cantilever beam, generally we get c1 and c2 value 0. Now put the value of c1 in this equation and put the value of x equal to 20 mm. So and then divide that right side answer by ei. Now value of e is given 210 GPa. So you need to take e equal to 210 into 10 raised to 3. and value of I, cross section is given, that is square cross section. So we can calculate we can easily calculate value of moment of inertia I equal to BD cube by 12. Okay, then divide this EI term in the right side, and then you will get the value of slope. Sorry, in this equation, sorry, in this second equation, you will get the value of slope in the second equation. Just put the value of x equal to 2 in this equation and divide by whatever answer you get in the right side, divide it by the product of EI only. You will get the answer for the deflection. This is the conventional method. You can solve this problem by standard cases also. Generally, most of the time, they ask for the standard cases, but if standard case is not given, you should aware of the conventional method. Do you understood? If anybody having doubt, please ask. Do you understood this conventional method to find out the deflection? Okay, now we'll see one problem for the shearing traces. Okay, generally weightage for the shearing traces is very less. In very few question paper, shearing traces, question on shearing traces in GATE 2009. Question is, for a given shear force across a symmetrical I section, the intensity of shear is maximum at extreme fiber, center of the section, at the junction of a flange and the web of web on the web, and last at the junction of the flange and the web but on the flange. So first I will draw the cross section, then you will understood. Symmetrical I section is given. This is the symmetrical I section where we will get the maximum shear stress, intensity of shear stress maximum. Where we will get the maximum shear stress? Do you have any idea where we will get the maximum shear stress? We will get the maximum shear stress. We always get maximum shear stress at the neutral axis, and this is the symmetric, so we'll get the neutral axis at the center. So we will get the maximum shear stress at the center of the section. Okay, center of the section. Then we'll see next question. The shear stress at the neutral axis in the beam of triangular section with the base 40 mm, and height 20 mm, subjected to shear force of 33 kilonewton each. So means we need to find out the shear stress at the neutral axis. This question from GATE 2007. So neutral axis for the triangular section is always from h/3 distance from the base or 2h/3 distance from the apex. Okay, and tau at a neutral axis means shear stress at a neutral axis is always equal to 8V, or we can say 8S divided by 3BH. V means shear force. Value of shear force is given 33 kilonewton divided by 3BH. B is a base is a 40 mm and height is a 20 mm. If we put the values in this formula, we'll get the answer. I will copy this formula. 8V, value of shear force is. So answer is in MPa, so we need to convert this 33 kilonewton into Newton. 33 into 1000. Divided by 3BH. Means base is a 40 and height is a 20. 40, height is a 20. Okay. Here also we can use conventional method to find out the shear stress at a neutral axis. Okay. But by formula directly we can find out the answer. 8 into 33 into 1000. 3 into 40 into 20. 3BH. 33 into 8 into 1000 divided by 240. Sorry, formula is 8 by 3. 8 by 3, right? 8 by 3 V by BH. Yes. So what is the answer? What is the answer? Answer is 10 MPa. Eight into 33. Okay. 3 into okay. Now we'll go for next problem. The cross section of a beam is rectangle 60 by 80. Shear force is a 144 kilonewton. Calculate the shear stress at the section 40 mm above neutral axis. Okay, the cross section of a beam is given, the rectangular cross section. So I will draw a rectangular cross section. 60 into 80 means base is given 60 and height is given 80 mm. So this is.
Hello, sir.
Yes.
Hello.
Yes, Yogiraj.
हा सर, मागच्या क्वेश्चनचा आन्सर पाहिला.
आन्सर एक मिनिट हा. 8 into 33 किती येते आन्सर, किती येते तुमचं? योगीराज
हाँ हाँ सर.
किती येते आन्सर किती येते
11.
11 ओके 11 मीन्स नियर अबाउट 11 येत असेल आन्सर त्याच्यामध्ये नियर अबाउट आन्सर 10 MPa आहे सो वी कॅन सिलेक्ट दिस सी ऑप्शन जर 11 येत असेल तर 11 नाही येते पण माझा आन्सर 8 into 33 because we need to calculate answer in MPa 8 into okay 8 into 33 we'll take 8 into 33 divided by 3 into 40 into 20 okay now we'll see the answer okay we'll see this question is from gate shearing trace okay we'll get the answer yes a shear trace at the neutral axis in the beam of triangular section with the 40 oh okay I have taken wrong shear force that's subject to shear force 3 kilonewton but here I have written here 33 okay now we'll get the answer you will get the right answer okay 8 into 3 8 into 3 into 1000 divided by 3 into 40 into 20 10 MPa now we'll get the answer here also I think same thing happen in this question we need to check the answer okay Yogiraj are you getting
Yes sir, yes sir.
okay now next question the cross section of a beam is a rectangle 60 by 80 shear force is a 144 kilonewton value of shear force is 144 kilonewton and we need to find out the shear trace at a section 40 mm above neutral axis 40 mm no sorry 20 mm below 20 mm we need to find out the 20 mm below neutral axis or yes above or below it will be same 20 mm above neutral axis okay so first we'll find out the neutral axis this is similar rectangle cross section means it's symmetrical about x-axis y-axis so this neutral axis will coincide with the centroid let this is the neutral axis I will write here neutral axis now this distance is 80 and this distance is a 60 I will write here distance 60 okay and this distance is 80 okay means neutral axis at a distance of 40 mm and we need to find out shear trace at a distance of 20 mm above neutral axis so here we need to find out okay I will take different section. I think in paint it will be very easy. Neutral axis, and then we need to find out the at 20 mm. Inside exact center. I will take different line. This is 60. Height is 80, and this is our section. Okay, I will take this diagram. Okay, now we need to calculate the shear stress at this section line, means at a 20 mm above from the neutral axis. Okay, so I will write the basic formula for the shear stress, that is tau. So I will write here tau equal to S A Y bar divided by IB. Okay, now S means shear force. Value of shear force is already given, that is 144 kilonewton. Okay, 144 kilonewton. We will convert it into Newton. Then value of AY bar. Value of AY bar. To calculate the value of AY bar, as per given statement, we need to calculate shear stress at this yellow line. Okay, so we need to consider area above the street. So we need to consider this much area. Okay, and center of this area will be at the center of a rectangle. Okay, so means a area is a area equal to 60 into 20. 60 into 20. And y bar equal to, value of y bar is important. Value of y bar is equal to value of individual center. Value of individual center. This is our considered area. Now center of a considered area is here at a distance of 10 mm from the top side, right? And y bar means this is the distance, means y bar, distance of individual distance of considered area centered from the neutral axis. This is known as a y bar. Okay, so this distance is 20 plus this 10, so this distance will be 30. So y bar equal to 30 divided by moment of inertia of whole figure, that is 60 into 80 cube divided by 12. 80 cube divided by 12. Okay, and divided by, sorry, into value of B. B is the strip width. This is strip width is a 60. Okay. Just do the calculations. I will keep proper bracket here. 60 into 80, 144 into 1000, right? 16 to 20 into 30, okay. Divided by I, moment of inertia is 16 to 20, 80 cube divided by 12 into 60. Okay, right. Now calculate the value of tau equal to 144 into 1000 into 60 into 20 into 30 into 60 into 20 into 30, and then 60 into 80 cube divided by 12 into 60 into 60, right? 33.75, 33.75 Newton per mm square. So this is the shearing stress at a distance of 20 mm from the neutral axis. So we can find out shearing stress at any distance from the neutral axis. Okay, just we need to take strip at that distance, and we need to consider area above the strip. If distance is given below the neutral axis, then we need to consider area below the considered strip. And basic formula, tau equal to SA y bar, that is SA y bar divided by IB. S means shear force. This A is the area of considered strip, and y bar is the distance of centered of considered area to the neutral axis distance, and I is the moment of inertia of a cross sectional area, and B is the width of a considered strip. So in this way we can find out the tau value at any section. Okay. Okay, do you understood? Yes, okay. Now we'll see the next problem. Just you can see this problem is similar to above problem. If a beam of rectangular cross section is subject to vertical shear force V, okay, here value of shear force given in terms of a V. The shear force carried by the upper 1/3 of the cross section is, means one third of the cross section. So here will be the neutral axis, and V is the shear force value, and we need to calculate value of shear force carried by the upper 1/3 of the cross section is, means suppose L is the length, then we need to consider L by 2 into 1 by 3 at that distance, means we need to divide this part into 3 section, 1/3. So if this distance is L by 2, we need to multiply by 1 by 3, and at this section we need to calculate the value of shear stress. So I will show you question of shear stress. Yes, here if a beam of the rectangle cross section is subject to vertical shear force V, the shear force carried by the upper one-third of the cross section. Upper one-third of the cross section is, okay, upper one-third of the cross section is, yes. So upper one-third means we need to divide this L into, sorry, total length into 3. Means we need to calculate shear force or shear stress at a distance of L by 3 distance from the top side. L by 3 distance from the top side. So this distance will be L by 3. L by 3. Okay. We take height. So we'll write here H by 3. We need to calculate shear stress at a distance of H by 3. So again use same formula, tau equal to SA divided by IB. No, not necessary. We know that shear stress distribution for this here should be maximum at extreme 0. Okay, we'll see the H by 3 tau equal to SA y bar divided by IB. But here beam dimensions not given. So how we can calculate? Yes, anybody having a idea about this, how we can solve? Yogiraj, how we can solve? Now here width is not given, height is also not given. The value of shear force for the rectangle cross section, how we can calculate? So we need to write basic equation. That basic equation is tau equal to, means we need to solve the derivation. So tau equal to, basic equation will get V by 2I is moment of inertia into d means depth, d square by 4 minus y square. Y square. Now in this equation we need to put value of y equal to h by 3. Sorry, value of y equal to 2h by 3 and value of d we can take here h y square Okay, this is basic to calculate the shear stress at any section for the rectangle section. Now we need to calculate at a distance of h by 3 from the top side, means we need to calculate this distance is h by 2 minus h by 3, and that value we need to take as a y distance. Okay, then we can calculate I equal to again bh cube by 12, and if we put the value we'll get the answer That answer is 80V by 27. Just try to solve it. Okay. You know, please fill up the feedback form. If you already fill up, you can leave the class. Please try to solve this question.